Alright, GLE 8s. How's it going? We're going to be doing our first math lesson here in our workbook. It's understanding rational and irrational numbers. Um, and these words might scare you a little bit, like irrational number or rational number. I know some of you might know irrational if you're like acting irrational. Maybe rational, it's like maybe you acted in the correct way. But in math, it's a little bit different, a little bit related. I'm assuming that you've already read through getting the idea and looked at some of these examples, so I'm just kind of going to build off of that right now. So rational numbers are all of these numbers that are also integers, counting numbers, and rational numbers. So counting numbers count as rational. Integers, which are negatives, 0, and positive numbers that are whole, count as a rational number. And also, fractions can count as a rational number. Decimals can count as a rational number. And negatives also count as rational numbers too. The important thing to remember about rational numbers is going to be in decimal form. So all of these, we need to be looking at them in decimal form. So rational numbers are numbers that have an end. Numbers that have repeating decimals. So those two things are so important to keep in mind. So they have an end, meaning I will give you an example. When we're looking at a decimal form, maybe 5.15. It has an end. It's not going to go on forever. Another example might even just be 4. It has an end. Even another example could be 7.32419, and it stops at 9. That's another example of a rational number. Also, rational numbers can have repeating decimals. So what that means is, I remember going over this in class, like if I had a 0.71 repeating with that sign on top, that bar over the numbers mean those numbers are going to repeat. So if I wrote this number out to a little bit farther, it would look like this: 717171, and it would keep on going and going and going forever and ever. It would not have a stop, but it would repeat. So because it repeats, it does not have an end, but it repeats, it also makes it a rational number. All right, so rational numbers, we look at them in decimal form. They have an end, and they are repeating. Irrational numbers do not have an end and do not repeat. So directly the opposite of our rational numbers. Irrational numbers do not have an end. So if you see this example they put, there's no repeating pattern that we can see. And it's going to go on and on and on. That's why there's that ... It never has an end in decimal. Pi is another really famous one. So it's like 3.9459 something. But it keeps on going and going. It does not repeat. It does not have an end. That's going to make an irrational number. So whenever you see this pi symbol or even this e symbol, you're going to be, oh, hey, that's irrational. That goes on forever and ever and ever. Also, sometimes the square root of numbers will have a decimal that never, ever ends. Actually, often the square root has that unless it's a perfect square. What I mean by that is, if I have a square and all the side lengths are 3, my area is going to be 9. So the square root of 9 is going to be equal to 3. So I can multiply by something by itself to get a number. 2, I cannot multiply something and itself to get 2. 1 times 1 is 1. 2 times 1 is 2, but 2 and 1 are different numbers. So 2 would be irrational. So that's kind of just an overview, the really important information from getting the idea. for the examples. I'm not going to go over the first few examples because I think they're self-explanatory. You can kind of just see if the decimal there is going to repeat, if there's an end or not, and that way you can tell if it's rational or irrational based on getting the idea. I do want to go over converting repeating decimals to fractions. So we know if a number is rational, it can repeat or have an end. We know how to convert ending decimals to fractions, but repeating decimals can be a little bit trickier. So this is how they do it here. We're going to use 0.27 as our decimal, and we want to convert that to a fraction. Step 1 says write an equation, let n equal it. So they just put n equals 0.27 repeating. That bar on top of the 7 means repeating. So that's going to be your first step, okay? Then we're going to write a new equation by multiplying both sides by 10 to the p, where p is the number of digits that repeat. Okay, that might sound confusing, but p is the number of digits that repeat. 7 repeats, that's only 1 digit. So, write a new equation by multiplying both sides, this is important, both sides, to keep it equal, by 10 to p. P is how many digits repeat. Well, this one we only have 1 digit repeat, so I'm going to multiply, I'm going to rewrite it and just do a little bit more step by step. So if n equals 0.27, I need to multiply this side by 10 to the first power because they have the digit of 1 that's repeating. 7 is only 1 digit that repeats, and p is that. So 10 to the 1 power, I'm going to multiply it on both sides of the equation. So n times 10 to the 1 is 10n, and then 0.27 times 10 to the first power. Every time I multiply by 10, I move that decimal 1 place. So this is going to become 10n equals, move it 1 place, 2.7. Repeating, so that's going to be repeating though. So that means this is going to be 7, 7, 7, 7, 7, 7, 7, all the way off the page. But I'm going to just keep it like this, look like 7 repeating. And that's just what step 2 has done. So it's going to be 10n equals 2.77777777 repeating. Let's move on to that step 3. So we have our equation that's multiplied by 10 to the p and our equation that's not multiplied by 10 to the p. The original one, we just said n equals the number that we wanted to use. So subtract the original equation from the new equation. It's very important to keep the place values in line. I don't want to be subtracting the wrong decimal places. Now, just to review real quick, we have place values here. We have this random number, 1.3418, and I see that 1 is the whole numbers. The next place value is 3, it's tenths, goes thousandths. The 4 is hundredths, then it goes thousandths, 10,000ths, and so on and so forth. The next one would be 100,000ths, then 1 millionths, and it would keep on going and going and going. But when we're doing these step 3, we want to make sure all of our values line up. You see how the tenths are with tenths, the hundredths are with hundredths, the whole numbers are with whole numbers on both sides of the equation. That's like that. So when we subtract them, I'm just going to start on this side of the equation. 7 repeating minus 7 repeating is 0. 7 minus 2 is 5. 2 wholes minus 0 wholes is 2 equals, and now we're going to do a different subtraction problem. So 10 minus 1n, 10n minus 1n, they have the same variable, so we can combine like terms. That's going to be 9n. So now I have 9n equals 2.5. Now all we got to do is solve that equation, and we'll have a good fraction for our n. Remember, what we started with in step 1, just said that n is equal to the number that we're using to get a fraction. So we want n to be alone on this side of the equation as well. So now we have solved for n. Write n as a fraction in the simplest form. So I have 9n equals 2.5. Well, I can divide each side. Here, I'm going to rewrite it just right here. Just to review step by step how to solve for n. I want to get n by itself, and it's being multiplied by 9 here. 9n is equal to 9 times n. To get n by itself, I do the opposite. I divide by 9 on each side. 9 divided by 9 is 1, and I still have n, so 1n equals 2.5 divided by 9. I don't know what that is. There's a decimal, so I'm going to keep it as a fraction or as a division. It's 2.5 divided by 9. I don't like having decimals in my fractions, so I can multiply the top and bottom by the same thing to get rid of that. So I'm just going to multiply top and bottom by, let's say, 2, because I know 2.5 times 2 is going to give me a whole number. So I'm going to do 2.5 times 2 is 5, and I have to do the same to the bottom that I do the top. Same thing, numerator and denominator. 9 times 2 is equal to 18. So 5/18 is going to be that fraction. I can't simplify that anymore, so we know that the decimal 2.7 repeating is equivalent to the fraction 5/18. I'm going to do one more example that has multiple repeating numbers. Okay, and then you can follow along with all the other examples in there. I'm going to do example 7, I believe. So we have convert 8.139 repeating. All 3 of these digits are repeating because the bar is over all 3 of the digits to a fraction. So that's step 1. Write it as an equation set to n. So I have n equals 8.139, all repeating. Remember, I have 1 digit, 2 digit, 3 digits being multiplied, or being repeated. Second step, we have to multiply each side by 10 to the p. Remember that p is how many repeating decimals we have. We have 3 repeating decimals, so I'm going to multiply this side by 10 to the 3rd power, and multiply this side by 10 to the 3rd power, each side. Remember, each time we multiply by 10, we move it 1 spot. So I have 10 to the 3rd power, that means 3 times. So move it 3 spots. 1, 2, 3. So I have 8,139.139 repeating equals, now this side, 10 to the 3 times n. Well, no, 10 times 10 times 10 is equal to 1,000. So I have 1,000 n's. And it's the same thing that we had written right here. All right, so our last step here, our 3rd step, is to subtract the original. Remember, we just wrote n is equal to 8.139 repeating from the new one when we multiply by 10 to the power of p. And p is how many repeating decimals we have. We have 3 repeating digits. So we're going to subtract them, and they set it up just like this. I'm just going to rewrite it off to the side so you can follow along. I have 1,000 n equals 8,139.139 repeating. Remember, we got that by multiplying each side by 10 to the 3rd. And then our original is n is equal to just, 8.139 repeating. I almost made the mistake I told you not to make. We have to line up each of our place values with the correct place value. So if I put it up here, that would be the thousandths place. I wanted that 8 on the ones place, so I'm just going to erase that real quick. 1,000n minus 1n, 999n. I have 139 repeating minus 139 repeating. That will cancel out, so I get a 0. Drop my decimal place. 9 minus 8 is 1. 3 minus 0, 0. 3. 1 minus 0 is 1. 8,000 minus 0 is 8,000. So I have 999n equals 8,131.0, or I can just eliminate that altogether. Make that a whole number. Now, to solve for n, I'm trying to get n by itself now. I have a 999 times n equals that. To get rid of this times 999, I got to divide by 999. 999 divided by 999 is 1n, so I'm just going to write n. And then 8,131 divided by 999. I'm just going to keep that as a fraction because holy crap, I don't know what that decimal is. And hey, what? Guess what? We're going to leave that like it is because it's simplified. The decimal 8.139, remember we set that equal to n at the beginning, is equivalent to that fraction because n is equal to that. So that's your answer. I'm going to do the coached example now, and then I'll let you do the lesson practice on your own. Remember, keep updating me on Jupyter. If I can help out with any more specific of the concepts, let me know, and I can just upload a video or do a video and upload it, or any clarifications I need to make in my videos. We can do that too. Okay. Write 9.268 repeating as a fraction. So I know I have to set it equal to n. So n equals 9.268 repeating. I'm going to put repeating over the 6, 8. The decimal has 2 repeating digits. 2 digits. 6 and 8 are the repeating ones. Write a new equation by multiplying both sides of the equation by 10 to the p. P is how many repeating digits? So it's 10 to the second power. Remember, 10 to the second power is 10 times 10. That's 100. So I need to multiply both sides by 100. N times 100 is 100n. 9.268 repeating times 100. We move that decimal point 2 spots. 1, 2. Every time we multiply by 10. So it's going to be 926.8. And then I need to include 6, 8 repeating as well, because it's going to keep on repeating. Remember, when we just move that decimal, we still have a 6, 8, 6, 8, 6, 6, 6, 6, 8. But since we moved the decimal, we're going to keep that repeating decimal at the end. Subtract the original equation from the new equation. So we have our new equation minus our original. 100 minus n is 99n. 6, 8 repeating minus 6, 8 repeating is 0. I'm not going to write anything. 0.8 minus 0.2 is 0.6. There's my decimal. I can't subtract 6 by 9. I got to borrow 1 from here. Make it 16. 16 minus 9 is 7. 1 minus 0 is 1. 9 minus 0 is 9. So I should have 99n equals 917.6. Got to get n by itself to do that. I got to divide each side by 99. 99 divided by 99 is 1n equals 917.6 divided by 99. I don't want any decimals in my numerator, so I got to multiply the top and bottom by 10 to get rid of it. So multiply by 10, move 1 spot, 9176 over, multiply by 10 on the bottom as well. 990 is my fraction. So I can reduce this by 1. So this is, we would put it maybe right here. So 9,176, sorry, divided by 990, or over 990. I can simplify that. I see they're both even, so let me just divide by 2 on the top and the bottom. If I divide the top by 2, 9,176 divided by 2, I get 4,588. On the bottom, 990 divided by 2, I get 595, and I'm not going to reduce that anymore. The decimal 9.268 repeating is equivalent to the fraction 4,588 over 595. Whew. Alright, that was a lot of work. If I went too fast, please just pause the video because I'm already 20 minutes deep here. All of these lesson practices should be related to the examples. Just look back through these examples. Stuff on Jupyter that might have stuff to fill in on tables and stuff, I'll say what to put in on Juno. So still fill in the workbook. On Juno, it'll only be part of the answer. So for number 8, I think I asked for all the rational numbers instead of just sorting them both. So you already do the work, you just have to plug in the answers into Juno. So pay attention to what Juno asked for, and good luck. All right, see you, kiddos.